Welcome back, everyone, for the second day of the tutorial. We are glad to have you here. And today we'll start with Chara. Chara, whenever you're ready, you can
go
ahead.
Excellent. Welcome back, everyone. This is the second day of the tutorial on incentive-compatible and incentive-aware learning. I am Chara Podimata, a fourth-year PhD student at Harvard, advised by Yiling Chen.
And I'm Nika Haghtalab, an assistant professor at Cornell University.
So just to give you an idea of the agenda of the things that we're going to be discussing today, we're going to start by where Nika concluded yesterday, which was Nika was considering machine learning when you have truthfulness as a basic assumption. Today, we're going to start off from there and try to achieve truthfulness or incentive compatibility with different mechanisms. So to incentivize truthfulness in machine learning. Then we're going to start talking about incentive-aware learning and specifically repeated Stackelberg games. And this is where we're going to have a break. Then Nika will talk to us about incentive-aware learning in Stackelberg security games, which, as we briefly mentioned yesterday, they are a subset of the Stackelberg games that we are considering. And then we will conclude the tutorial by briefly talking about the research agenda that has emerged for strategic classification. And we're going to have some discussion about open directions, about moving beyond the standard models. So let's start. And again, I'm going to be talking about incentivizing truthfulness in machine learning algorithms. And this actually has been a topic of great interest, both in the econ-CS or game theory community and the AI or machine learning community. And that is also visible by the fact that all of the papers that have to do with incentives as robustness tools have appeared in a variety of conferences, some of which are AGT oriented, others are learning oriented, others are OR oriented, as we will see in a couple of slides afterwards. Just to give you a broad idea of what has been studied so far in the space of incentives as robustness tool, there have been works that study linear regression. Why is linear regression so important? Well, remember the Chara example that we talked about yesterday? These papers are centered around incentive compatibility, but there have been other considerations that people care about, for example, different equilibria in linear regression and so on. There have been papers on classification and in fact strategy proof classification. There has been one paper that shows the impossibility of strategy proof clustering, a recent work on incentive compatible active learning, two works on prediction with expert advice, and works on univariate estimation and information elicitation for statistical inference. And by the way, I'd like to point out that this is a non-exhaustive list potentially, but I just wanted to give you an idea of what people are interested in on this space. And for the first 10 or so minutes, probably 15, I will be talking about the problem of prediction with expert advice as modeled by two papers, one by Ralph Garden and Shrivers in NeurIPS 17, and one paper that I co-authored with Rupert Freeman, David Pennock, and Jen Wortmann-Vaughan that is about to appear in this year's ICML. So let's start with the problem overview. And let me remind you actually why incentives in prediction matter. We briefly touched upon that yesterday, but let's review the examples here. Imagine that you're a learner and you want to predict the probability of an event happening on the next day. And for concreteness, I'm going to be thinking about as the learner being the Good Judgment Project, who was one of the competitors in IARPA's geopolitical forecasting competition. And you want to predict the probability of the number of COVID-19 patients in the US going up in the next day. And to do so, you have access to a number of forecasters who give you predictions about this probability at each day. So for example, these are the predictions that the forecasters give for the first day. These are the predictions that they give for the next day, and so on and so forth. Now, the learner's goal, Good Judgment's goal, is to learn how to make accurate predictions. And in order to motivate the forecasters to put their best effort and try to give as accurate predictions as possible, they reward the forecasters with special perks for their performance. And to be concrete, in the Good Judgment Project, the top 2% of the most accurate forecasters are given the super forecaster credit, and they have extra perks because of that. Now, the problem that these motivations, these perks have, is that they might actually create perverse incentives from the perspective of the forecasters. What do I mean by that? If you are a forecaster that you believe very highly, with probability 80-20, that the number of COVID-19 patients will go up in the next day, then you might have an incentive to actually tweak your predictions a little bit. Why? In order to increase the perks that the Good Judgment will give you if actually the event gets realized as you were hoping for. And this is not only created as a result of like this forecasting competition that the Good Judgment runs, but this is also the case in a website that's very well known to many of us, and I'm sure we will be monitoring it very, very closely for the next couple of months. This is also true in 538. Here's why. 538 collects the predictions from different pollsters and somehow aggregates them. I'm going to talk about this somehow in a minute. Somehow they aggregate them, and then they issue their own forecast about the election or about the politician's likeness and stuff like that. Now, this aggregate, the way it happens is that each of the pollsters has a weight that is attached to their name. And this weight is something like a reputation token. And it's due to the fact, it's like the accuracy grade that 538 has given to this forecaster, which is also shown publicly in 538's website when they explain how their aggregate is produced. So if a forecaster, for example, knows that most of the forecasters around them believe that politician A will almost certainly get elected, while they have evidence that politician B will get elected, because they are afraid of the grade that they will get, they might actually try to side with other pollsters in order to try to game the estimate of 538. And just to put this into a little bit more concrete of a mathematical model, and I'm going to start off by the model that we considered in our ICML paper. There's a repeated interaction protocol between a learner and experts at each event, T, in a number of events, capital T. There's a set of K experts, each of which reports a probabilistic prediction about the event. So this, for example, corresponds to the probability that each forecaster gives about the number of COVID-19 patients going up in the next day. Then I maintain some probability distribution over the experts. And with this probability, I choose one of the experts. Then the event is realized. So this is actually the number of patients that, the COVID-19 patients that the US registers in the next day. And every prediction has an associated proper loss. That is both the learner's prediction and the expert's prediction. And the learner updates their probability distribution that they maintain over the experts. And again, the goal of the learner is this notion of regret that Nika introduced to us yesterday, which is the difference between the cumulative loss of the algorithm's choices minus the loss of the best fixed expert in hindsight. And we want this to be sublinear in T. And now, just to put things into perspective, up until this point, I have basically reintroduced the model of learning with expert advice, which Nika talked about yesterday in the context of learning hypothesis classes. Okay, so at this point, this is the standard online learning prediction with expert advice problem. Now, what makes this problem distinct when we're talking about strategic agents? Well, experts now strategically can report their prediction. And why would they strategize? Well, they want to strategize because they want to ensure that the prediction that they report now can help them maximize the probability of being chosen at the immediate next round. So they're not farsighted. They can only play something now in order to alter the weight that the learner assigns them at the immediate next round. And I have already mentioned that we will be talking about, Nika mentioned yesterday that we focus on full information or partial information settings. When we are talking about the quote unquote prediction with expert advice problem, full information is when you can actually observe all of the reports of the agents, and partial information is when you can only observe the report of the expert that you choose to play at the particular round. And because I mentioned that, Ralph Gardner and Shrivers, in a very nice paper at NeurIPS 2017, they considered a similar model, but similar to what we talked about yesterday. Remember that what differentiates different strategic learning models is the assumed utility that the agents that they have want to maximize. So just to give you evidence of that, Ralph Gardner and Shrivers consider the following problem. Instead of this probability that the learner places on choosing each expert comes as weights as essentially the normalized weight that the learner maintains over the experts. They do not consider proper losses. They only talk about the absolute loss function. They are not interested in agents that want to maximize their probability of being chosen, but only their unnormalized weight. And finally, the guarantee that they are aiming for is slightly more relaxed than ours. It's the guarantee of alpha regret. And just to be ahead of any potential questions, none of these two works subsumes the other. We should think of them as kind of distinct because of this difference between the two loss functions that we consider. So proper loss functions are a quite different family compared to just a single absolute loss. They pose a technical restriction, but they include way more loss functions. Yeah, so we can discuss more about that either in the break or afterwards. Feel free to ping me. Both of these works, however, both ours and the work of Ralph Gardner and Shrivers, they wish to address this question that is at the heart of this first part of today, which is that whether there exist online learning algorithms that are both no regret, with whatever notion of regret you define, and incentivize the experts to report their true beliefs. And remember that, as we talked about yesterday, we call these algorithms incentive compatible. And the thing that I'd like you to get out of this day is why strategic learning settings are so different than standard online learning settings. So the first question that one should ask when faced with such an incentive compatible or incentive aware problem is, why not apply a standard online learning algorithm and try to see what happens in the strategic setting? So what do I lose if I just apply a standard online learning algorithm in this strategic prediction problem? Well, what would you do? Nika introduced to us yesterday the multiplicative weights update algorithm, which is due to the celebrated paper of Freund and Shapiro in 1997, which achieves the optimal regret guarantee, which is square root t log k. Now, why can't you just apply this algorithm to solve our problem with the double constraint that you want both no regret and incentive compatibility? Well, if you try to do so, you'll end up having an algorithm that's not incentive compatible. And actually, this is not just the case for multiplicative weights, but we can actually show misreportings and manipulations for algorithms that are like gradient descent, for example. Okay. And so what can we do in this case? How can we protect ourselves? Sorry, I'd like to stop here because I see two Q&As.
Question.
Yes.
So Eric is asking whether it makes sense to aggregate experts' probabilities by taking like weighted average, for example, rather than having.
Correct. It makes 100% sense. So the results that I will be presenting in this work, they aggregate their reports only, so we have only experimental results for that. So yes, it's, yeah.
Great. Another question, Greg is asking if you could provide a little bit more intuition as to why experts will act strategically and why don't they just try to minimize their own profit loss in a way?
Because, so back to the, how can I say that? Let's look at back to the let's look back at the Good Judgment project. So if you try to minimize your proper loss, what would have happened was that you would try to be incur as small loss as possible. But it's not that when you have this as small loss as possible, it's not that it directly translates into you being the best, you being the one that the algorithm chooses. And to see that, go back to what Nika was describing yesterday about follow the leader. So follow the leader is good in the sense that, yes, it chooses the most accurate forecaster, but it suffers from linear regret. And that's known, so that's why you never follow exactly the most accurate expert. So you always add a probability of not following them, or like a perturbation. And this perturbation or probability of not following them is what essentially creates these perverse incentives.
That's it for now. You can continue.
Okay. So working with this model, in this paper, we showed that you can actually achieve both incentive compatibility and full information no regret algorithms, and also incentive compatibility and bandit information algorithms. And I'd like to stress one thing here, that for the full information case, which is the model I've been implicitly describing so far, it seems to be the case that we lose nothing in terms of guarantees compared to the standard multiplicative weights update algorithm. So see here, the regret guarantee of the family that we introduced weighted score update is exactly equal to the guarantee that multiplicative weights update gets, which is rather surprising, right? Because we put an extra layer of constraint to our algorithms. We want them to be not only no regret, but also incentive compatible. And yet we can achieve the optimal regret guarantees as the non-IC algorithms would achieve. That's not so, the story is not so positive in the bandit information case, where the algorithm family that we suggest suffers from a regret guarantee that's t to the 2/3, which is strictly worse than the guarantee for EXP3 that Nika talked to you about yesterday. And it's actually one of our interesting open questions, whether there fundamentally exists such a gap between the incentive compatible and non-incentive compatible settings. And just to give you an idea about how we achieve that, and hopefully this will be an idea that can help prove similar guarantees for other online learning problems, I'll walk you through the seemingly unrelated problem of wagering mechanisms. Now, in a wagering mechanism, there's a mechanism designer who wants to predict the single-shot probability of a recession occurring in 2021. To do so, they have access to a number of forecasters, and each of the forecasters give the expert or the learner, the mechanism designer, information in the form of tuples. The first part of the tuple is a probabilistic prediction according to which they think that a recession will occur. And the second part of the tuple is a monetary wager that they are ready to stake in order to support their prediction. Now, the mechanism designer collects all of these tuples. She observes whether a recession happened or not, and then she redistributes money in the form of payments to all of the experts according to their accuracy. And observe here that contrary to the individual rationality that we talked about yesterday, in this example, it might be the case that a forecaster loses money by playing the game. So for example, for the green forecaster here, enters with a monetary wager of $20, and they end up leaving in this case with only $15. Now, in a seminal paper, Lambert et al. In EC'08, they suggested the family of weighted score wagering mechanisms which satisfy two very important properties. On the one hand, they are incentive compatible, and on the other hand, they are strictly budget balanced. And what does this mean? It means that the amount of money that the mechanism designer collects in the form of wagers prior to the run of the mechanism is exactly equal to the amount of money that the mechanism designer gives back to the forecasters in the form of payments. And here's why these two properties are super important. I'll try to actually explain to you the whole paradigm of online learning as a wagering mechanism. So in standard online learning, you maintain a probability distribution over your experts or forecasters or agents, you call them however you want. Then you collect the reports and you observe the outcome realization. And then you redistribute the probability among these experts. And I hope that my language made it clear to you that you could actually view the original probability distribution as the wagers that the agents, quote unquote, give you, and the probability distribution at the next round as the payments that you give back to these agents once the mechanism is completed. Now, this means that if you use a wagering mechanism to update your distribution over experts, you directly have incentive compatibility by the family that I just discussed about in the previous slide. Well, what is the catch? You no longer have no regret. So if you just apply black box algorithm, the weighted score wagering mechanism, you end up incurring linear regret in the online learning problem. So here's what we did and what solved the problem for the full information case. We said, let's still think of the distribution of the previous round as a wager. We collect the reports and the event realization. And then in order to compute the distribution of the next round, we create two things. One is we create the convex combination of two things. One is one part is dependent on the weighted score wagering mechanism, and the other is dependent on the original probability with which we started, okay? And this is pi t plus 1, and we call this family of mechanisms, weighted score update algorithms. And now I want you to pay attention to this eta here, which has a dual meaning. The first meaning that it has is that it could be interpreted as agents placing the eta fraction of the wager in order to be judged by the weighted score wagering mechanism, which means that if you think about eta playing this role, you can directly have incentive compatibility. Why? Because the only way that someone can quote unquote misreport is whatever gets into the weighted score wagering mechanism family, which is, however, incentive compatible. And the second meaning that eta has is that it's known as the learning rate or the step size in online learning, which means that if you actually tune it properly, you can achieve no regret algorithms. And we're very happy that actually the no regret that we achieve is the optimal that you can have in this case. And before I move on, I'd like to see if there are any questions here about like the connections between like wagering mechanisms and online learning. I'll also give you a bit about what happens in Bandit settings and how you can use wagering mechanisms in Bandit settings too. But if there are any questions, I'd be very happy to take them.
There are currently no questions on Q&A or chat, but please feel free to ask questions if you have any right now.
I'll pause again when I conclude the section in incentive compatible online learning. So, I see a question.
The question is, what constraints should EDA satisfy to minimize regret?
Excellent. So the constraints is actually quite similar to, not quite, it's almost identical to the constraint that, oops, wait, my slides became possessed. Okay, so the constraints that they satisfy is, if I'm precise, square root log k divided by t. There might be some constants in front of there, but I do not remember them exactly right now. And it's quite interesting that it's exactly the same constraint that multiplicative weights update requires for EDA, as Nika showed you yesterday in the context of learning hypothesis classes. Yes? Should I move?
That's it for now. You can move.
Excellent. So, okay. So, and this actually goes to Hermes's question, let me give you like a vignette of why this ETA suffices, just a broad overview. If you actually analyze this convex combination of the weighted score wagering mechanism and pi t, you end up having this form here that I have in blue, which is essentially, you say that the probability for the next round is the probability that I had now, multiplied by 1 minus an ETA fraction of my loss, minus the weighted loss of all the other experts. And if we call this capital LIT, you see that there's a connection with the standard multiplicative weight update algorithm, but the only difference is that we are talking directly about probabilities, while the standard multiplicative weights update has to pass through the unnormalized weights. But for our case, because we're working directly in the space of probabilities, which has not been studied prior to our work because the proof is like slightly simpler, you only need to analyze, instead of going through the whole potential argument that Nika mentioned yesterday, you only need to analyze this case that I have here, that the probability of the optimal agent around capital T is less than 1. And why? Because this, if you actually expand this loss function, you'll see that the summation of Li star T for all rounds T equals exactly the regret that this algorithm incurs. And this gives you a novel and much simpler proof. And this is due to incentives, and it's all by itself. It's really interesting that you can actually have such an algorithm that's concurrently incentive compatible and no regret with a much simpler proof than the standard potential-based arguments. And as promised, I wanted to give you a hint about the Bandit case. So again, the question that we should always ask ourselves when we embark to strategic learning settings, why not use the standard tricks of substituting the real losses with unbiased estimators? Nika talked to you about this trick yesterday when she was introducing the Bandit settings. Well, if you try to do that, what breaks is surprisingly weighted score wagering mechanism. It's no longer incentive compatible. And even if it was, if you try to use the same update rule as we had in the previous slide, your probability that you give to each agent is strictly outside of the interval 0-1. So it's no longer a valid probability distribution. So here's how we tweaked that. We said that, okay, keep the previous update as you have it, and make sure that you always lower bound the probability so that you are safe, so that your probabilities never go out of where they should be. And this was our new update rule. We call this family the weighted score update with uniform exploration. And through some technicalities that I would like to not go into right now, we showed that this suffers a regret of T to the 2/3. So this is worse than EXP3, but this is incentive compatible and TXP3 is not. Yes? I see there is a question in the Q&A.
Yes. So
okay.
Asking, suppose you keep the setting that experts want to maximize the probability that they're chosen in the next round, but now experts have different levels of expertise. Could it make sense to also elicit some sort of confidence from the experts and kind of combine these PITs with this wagering and determining like what would be the rule?
Excellent. So we definitely have not looked into that in the current setting. And I'm actually not even aware of whether in the standard wagering mechanism literature, you can actually incorporate a confidence in these mechanisms. So that's super open-ended, and it would be great if somebody can look into that afterwards. And there was another question about the Bandit setting that I saw, and it's actually one of the open questions. We do not know whether it's tight, but what we do know is that it looks awfully like the coin betting setting without getting into too much detail. And in the coin betting setting, according to discussions that we've had with the coin betting people, they do achieve the same regret. So like it's like two settings that have similar properties and achieve for the Bandit setting this T to the 2/3. And these people are definitely more senior than for the mies for this space. So like, yes, if you could lower this, it would be great. And one more thing here, in the experiments that we run, the weighted score update with uniform exploration performed identically to EXP3. Now, I don't want this to give you too much hope, because it might have been that the real data that we collected from 538 were just so that they didn't have worst case instances, but I just place it out there. And let's talk about some open questions that we have in this space. There's a general theme, sorry, of measuring the price of incentive compatibility in online learning. So for the full information case, our algorithm, as I told you about, performs optimally and is IC. This is actually the question that we just answered right now. We, for weighted score update with uniform exploration, we do not know whether it's tight. So, and we do not know whether it's even possible to achieve the EXP3 type of regret guarantees. In the standard online learning setting, and that was also a question that came up yesterday, Nika touched upon, you can achieve guarantees that scale with the loss of the best fixed expert in hindsight. And we have no idea if that's possible for no regret and incentive compatible algorithms. And that would essentially say that you, instead of scaling with the time, you scale with the loss of the best forecaster. And another question that I'm super interested in figuring out is whether the wagering interpretation can help you build incentive compatible gradient descent type of algorithms. As I told you, we can definitely create manipulations for gradient descent, but we have no way of creating, so far, of creating incentive compatible algorithms. And the second theme is moving closer to fully forward-looking agents. And I briefly mentioned the experiments that we run previously. This is from a data set that we collected from 538. It's publicly available on their website. Now, this is the weighted score update algorithm that I've been talking about. And these are the state-of-the-art, but not incentive-compatible algorithms. But this algorithm, the dark line, is a variant of the algorithm ELF that was created by Witkowski et al. On a paper in AAAI 2018. That is, the variant that we have is incentive-compatible for forward-looking experts, which means that the expert can try to misreport at round T and have as their goal to maximize their probability of being chosen around T plus whatever you want, 1,000, right? I don't care. Now, this variant is guaranteed to be incentive compatible, and in experiments, it seems to have a great dependence in the number of experts, but the data sets were too small to actually get anything more meaningful than that. So the two major questions here are whether we can actually achieve theoretical guarantees for this algorithm, and whether there are any other forward-looking experts, algorithms for forward-looking experts that I'm not aware of. And with that, I conclude the discussion in incentive-compatible machine learning. Please let me, I see a question in the Q&A. Gary, could you explain again if at every iteration the event could be observed? At every iteration, the event after the event happens, it is observed by both the expert and both the learner and the experts. And with the wagering mechanism, incentive compatibility is satisfied. What does it mean by full information setting at Bandit setting? The full information setting for the prediction with expert advice problem is when the learner gets to observe the predictions of all forecasters. For example, in the 538 example, you get to see the polls of all the pollsters. In the Bandit setting, you get to see only the weight of, you get to see the poll of only one pollster, the one that you choose according to your probability distribution. I understand it by the loss of each expert could be observed. Yes, this is exactly what you say there. I understand it by the loss of each expert could be observed at every iteration. That's exactly the full information and Bandit information. That's the full information case. Okay, And unless we have other questions, in the incentive compatible online learning part of the tutorial, we're gonna switch gears a bit, and we're gonna, oh, there are 2 more Q&As. But the learner does get to observe the prediction of every expert when it applies the wagering mechanism or market prediction right. Excellent question. In the full information case, you do get to observe everything and build your wagering mechanism with the predictions that you saw. In the Bandit information case, we created a variant of the weighted score wagering mechanism that works only for unbiased estimates. So that was the non-trivial part of why we made this extra reweighting with the uniform exploration. Okay, could you get stronger? I think this is answered, but please feel free to ping us again. Could you get stronger incentives if you suppose that some of the experts aren't strategic? Excellent question, Greg. So this is interesting, right? Because this goes to, whether you have to also know who are the strategic agents and who are not, because otherwise you will use an algorithm that's not robust to strategic agents in the rounds that you see strategic agents. Now, I don't want to be dismissive of this question because it's excellent and it hasn't been addressed completely in the strategic learning literature. We namely do not know what can happen if our agents are mixed. Like if we have some strategic agents and some others that behave, adversarial, let's say. Could you explain more about the Bandit setting? In particular, how to apply the wagering mechanism from the expert setting to the Bandit setting. Since the Bandit setting, the learner can only observe the input from one expert. Yes, this is what I tried to briefly touch upon in the previous question that I said about the Bandit setting. We created a variant of the standard weighted score wagering mechanism of Lambert et al. that works with unbiased estimates. And what is the unbiased estimate that we built? The unbiased estimate that we built is almost identical to the estimates that Nika talked about yesterday. Loss of your observed loss of the agent divided by the probability that you play them. I think it's rather technical to go into the more detailed description of how like this algorithm works, like the technicalities. I'd be more than happy to answer questions during the break, but I feel that this goes a little bit beyond the scope of this workshop, the tutorial. Okay. Excellent. Thanks, guys. It's wonderful that we have a lot of questions.
Yeah.
Okay. Yes? Go ahead, Nika.
No. Go ahead.
So moving on to the incentive-aware part of our tutorial, I'd like to bring to your attention that there has been a lot of work that's been done, especially in recent years, regarding, for example, dynamic pricing, Stackelberg security games that Nika is going to talk to us about, profit maximization, and even solving linear programs. And there's a special place for strategic classification that there's a dedicated slide and discussion to follow. Now, before we conclude with this part of the tutorial, I'd like only to bring to your attention what a repeated Stackelberg game looks like, and then Nika will tell us more about these. So in a Stackelberg repeated game, there's a leader called also the learner and an agent who is the follower. And for each round T, the learner commits to an action. Now this action can be a classifier or a deployment of resources. Let's see. The agent has some utility that, very importantly, it's unknown to the learner and it depends on the learner's committed action. And according to this utility, they decide how to best respond to the action that the learner played. The learner gets to observe only this best response. Importantly, the learner, again, I stress this out, they cannot observe the utility. the learner incurs loss that depends on the action that they deployed and the agent's best response. And the benchmark, the guarantee that we are trying to optimize in these settings is the guarantee of Stackelberg regret, which was first discussed in the wonderful paper of Balkan, Blum, Haghtalab, Prakacha in EC'15. And it was formally defined in the very nice paper of Dong, Roth, Sujman, Wagner, Wu at EC'18. It's the notion of Stackelberg regret, which, and I want you to contrast this with the notion of external regret that Nika talked about yesterday. So in Stackelberg regret, what we are trying to optimize is the difference between the loss of the learner, if you give the opportunity to the agents to best respond, minus the loss of the learner of the best fixed action in hindsight, but had you given the opportunity to the agents to best respond. Now, contrast that with the external regret guarantee, which would do the following. It would compute the best fixed action in hindsight, alpha E star, had you not given the opportunity to the agents to best respond. So the only thing where these two loss functions, these two guarantees differ is this benchmark. And we saw a couple of details yesterday in the exercise session, namely that it's not as easy as we thought to just always minimize the external regret and try to achieve meaningful guarantees for Stackelberg regret, which imposes one of the great problems in repeated Stackelberg games, that this is the reason why you cannot apply standard online learning algorithms, and you need to do something that caters to the incentives of your agents. And Nika will tell us more about for the setting of Stackelberg security games.